Hi, my name is Adrián Corochano, and I am a PhD student of the ModelFLOWs group and a contributor of the ModelFLOWs app. In this video, I am going to introduce you the hybrid deep learning models. These tools are used for prediction in the deep learning module. To encourage you to use this application and more specifically this tool, I am going to show you the latest publication when we apply this tool to predict a combustion problem. In this paper, here you have the link, we apply deep learning architectures combined with sample processing techniques for temporal predictions in laminar reacting flows. As a brief explanation of the methodology, the algorithm consists on three main steps. Firstly, the variables of the database are preprocessed. This step is really important in combustion databases as the order of magnitude between variables varies a lot. In this case, the preprocessing techniques are the centering and scaling. Then, singular value decomposition is applied. More details about this decomposition method can be found on the corresponding video of the app. From this decomposition, we take the temporal coefficients and introduce them into the deep learning architectures. These neural networks will give us the predicted temporal coefficients, which will be used for reconstructing the predicted snapshots. The deep learning models used are a recurrent neural network and a convolutional neural network. These are a sketch of both models. This algorithm has been applied to predict an axisymmetric time-varying non-premix laminar co-flow flame. In this case, the fuel is injected below and is composed 65% of methane and 35% of nitrogen, and the oxidizer is air. From this simulation, we have extracted a snapshot tensor, which is a four-dimensional tensor composed by the variables, the spatial dimensions, and the temporal one. Here you have detailed the number of points in each dimension, and from these 999 snapshots, we separate them between the testing dataset, which is the 20% for testing snapshots, and a training dataset, which is composed by a 65% of training snapshots and a 15% of validation snapshots. Here in this algorithm, there are a lot of parameters to calibrate. In the first step, we have to calibrate the scaling method. In this case, we have used auto-scaling, which uses the standard deviation as the scaling factor, but there are several scaling methods implemented. On the second step, there are two parameters to calibrate. The first one is the number of modes to retain. Here we have to take into account that the first modes in the SVD retain the largest scales and the main dynamics of the database. Also, there is a scaling method to use in the temporal matrix, and here we have used a max per mode. On the third step, we have the hyperparameters of the deep learning architectures. First, we have the batch size. In this case, we have used 12. The activation function for the hidden layer, we have used ELU. The activation function for the output layer, we have used the parabolic tangent. The loss function, in this case, we have used a physics-aware loss function, which uses the relative root mean square error and takes into account that the sum of species has to be equal to 1. But there are others implemented on the app. And finally, the learning rate, which in this case is 0.005. Using this algorithm and trying to predict the temporal coefficients in the reacting flow problem, we obtain these predicted modes, and we can see that both models predict pretty good the modes, but the LSTM, the recurrent neural network, has the lowest error. If we go now and we see the predicted snapshots, we can see that the model predicts both the major and the minor species. Here in the link, you can see more information about the paper. Thank you for watching. If you have any comments or you want to know more about our group, please visit our website.